Okay, so this is F for Q4. First, we're going to draw a free body diagram for M1. So first we have Fn, M1, and then we have F of G, M1, and we have a tension 1, and then a smaller tension 2. Part B. Just doesn't want to work. We have an M2 with an Fn2 and then an FG2 and then a T2C. Calculate period T, so we can use Vm2 equals C over T. We're solving for T, so we set it, flip both sides, inverse both sides. T over C equals 1 over V2, and that's T equals to C over V2, which equals to 2 pi, and we use the R on the outside, the greater R, because it's the outside block. So T equals 2 pi 0.75, and they gave us velocity for the outside block, which is 4, and that is equals to 1.178 seconds. D. So one of the tangential speeds, so it's V1 equals C over T. Want the inner block this time, so that's V1, that's T1, 2 pi R, and then we use R1 this time since the inside block, and then T. And since the blocks are connected by a string, we know that the blocks will travel one revolution in the same time, just at different speeds. So it's 2 pi 0.4, the smaller radius, over 1.178, and we get V1 equals 2.1335 meters per second. E. Derive an expression, so it's AR equals V1 squared over R1. We know that V1 equals C over T, which equals to 2 pi R1 over T. So that's just AR equals to 2 pi R1 over T. The whole thing is squared, and all over R1. So AR equals to 4 pi squared over R1 squared. Wow, my Apple Pen is not cooperating. Over T squared over R1. That means that AR equals to 4 pi squared R1 over T squared, my bad, not T2. Okay. Next is F. So we want the ratio. So first we can just solve for ACM1. And we know that's just equal to V1 squared over R1. And we found V1 earlier to be 2, so that means that's just equal to, so that's just equal to 2.1335 over 2 squared over 0.4. So ACM1 just equals to 11.38 meters per second, and ACM2 equals to V2 squared over R2, and and that's just equal to 4 squared over 0.75, and that just equals to 21.3333 meters per second squared. My bad, that's squared there. So for the ratio, it's just M1 ACM1 over A CM2, and that's just 11.38 over 21.3333, and the ratio would be 0.5334. Now on to G. So for FC, we know that FCM1 is just the mass, which is 0.0. So write it out first. We know that it's just mass times acceleration, AC1. AC1. And so then that would just be 0.05 times AC1, which is 1138. Which is equal to 0.569. FCM2 equals to just M2 AC2, which equals to 0.03 times 21.3333. That means that FCM2 is just 0.64. We want the ratios, so we set them over each other. M2, that should be 0.5. Oh, that is weird. 569 over 0.64, and that just equals to 0.889. H is next. So magnitude of tension T, it's just FC1 equals to, we just set the net force, so FC1 equals to T1 minus T2. Solve for T1, T1 equals to FC1 plus T2. And we know that FC2, which is this is net force at the second block, is just equal to T2. So that means that T1 is just FC1 plus FC2. And we already found both of those earlier. So T1 equals to 0.569 plus 0.64. And T1 equals to 1.209 newtons. For I, it's easy too. These want T2. We know that FC2 equals to T2. So T2 is just equal to 0.64 newtons. Net force of the inner block, the magnitude, we know that it's just FC1, and FC1 we know equals to 0.569. K, J, oh, this is K. Lastly is K. Okay, so then if you increase the mass, we'll keep everything else the same. Okay, so we can, first I'm gonna set up the net force for each tension. Not the net, so the formula for each tension, which we found already, plus FC2. And if we expand this, it's MV1 squared over R1 plus MV2 over R2. Same thing with T2. FC2 equals to M2 V2 squared over R2. And we see here that, so that means that when we increase mass 1 and mass 2, while speed and R are the same, we can see that on both equations, both masses are on the top in both equations. So both tensions T1 and T2 will therefore increase.